All right, guys, I want to work through this review sheet for you, and the directions here on the first problems that we're looking at are to perform division by whichever method is appropriate. In this particular one, we're only going to use long division because we're dividing by a linear factor, but our leading coefficient is not 1. We would want this to be just like x minus 9 to use synthetic division. Because it's 4x minus 9, we're going to use long division. So 4x minus 9 divided into 4x to the fourth, 45x cubed plus 57x squared plus 18x plus 77. Being very careful to make sure that all of your powers of x are represented. If not, you have to have a zero placeholder. So 4x to the fourth divided by 4x is going to give us x cubed. I get that by dividing 4x to the fourth by 4x. That gives me x cubed. The next step in the long division process is to multiply. So we're going to multiply x cubed times 4x and get 4x to the fourth. X cubed times negative 9 is negative 9x cubed. The next step is to subtract, which changes the signs of these terms. So 4x to the fourth minus 4x to the fourth is gone. Negative 45x cubed plus 9x cubed is negative 36x cubed. And bring down the next term, 57x squared. Now we start the process over again. 36x cubed, or rather negative 36x cubed divided by 4x, right, is negative 9x squared. And then we're going to multiply negative 9x squared times 4x minus 9. That gives us negative 36x cubed plus 81x squared. And subtraction changes the signs. That's the part where you got to be really, really careful. Most students mess up on this test. So 57x squared minus 81x squared is negative 24x squared. Bring down the 18x. And then we do it again. Negative 24x squared divided by 4x is negative 6x. Multiply negative 6x times negative 4x minus 9, times 4x minus 9, and we get negative 24x squared plus 54x. And subtraction changes the signs. 18x minus 54x is negative 36x. Bring down the 77. And we got one more to do here. Negative 36x divided by 4x is negative 9x. Excuse me, just negative 9. The x is canceled there. Then negative 9 distributed there would give us negative 36x plus 81. And subtraction changes the signs. Looks like we have a remainder of negative 4. So my remainder is negative 4 over my divisor, which is 4x minus 9. So the quotient of this problem is x cubed minus 9x squared minus 6x minus 9 plus negative 4 over 4x minus 9. So that's how the long division process works. Let me skip. We're going to erase this one. So if you want to look at this a little more, you can pause the video. But I'm going to move on to the next problem. The next problem is, cancel that. So the next problem is this one. Now this problem is set up nicely to use synthetic division because we have a linear divisor here. This is a linear divisor, n minus 5, and my leading coefficient is 1. So it's 1n minus 5. I'm going to use synthetic division. The root of the divisor is 5. So I'm going to use 5. 8n cubed, negative 37n squared, minus 16n plus 3. We don't need the plus sign there. It'd be okay if we had it. Skip a line, draw a line, bring down the 8. Now, again, with synthetic division, you have to remember that every power of x is represented. So now we're going to multiply and add. 5 times 8 is 40. Adding there gives us 3. 5 times 3 is 15. Adding there gives us -1. 5 times -1 is -5, which means we have a remainder of -2. All right, so the quotient then, because we're dividing n to the third by n to the first, our quotient is going to be n squared. So that starts with 8n squared plus 3n minus 1, plus the remainder is -2 over the divisor, which is n minus 5. So synthetic division is a little bit neater and quicker process when it applies. That's number 2. Looking at number 3, I'm not going to work this one through, but just to point out that on number 3, you would definitely need to do long division because the coefficient here is not 1n. So that means it's long division. Now, there is a way that you can use synthetic division, but just the root of this is 7 over 6. The root of this divisor, and if you're having to do a lot of fraction work, it can get complicated. So it's just easier, and then there's also another step that you have to put into the end. So it's just a little easier to remember that if that leading coefficient is not 1, to use long division. Next problem, number 4, is again a good candidate for synthetic division. You've got a linear divisor with a leading coefficient of 1, so use synthetic division and the root there. The root is -9, and then you would do the coefficients. Again, making sure that you have every power represented, 4th, 3rd, 2nd, 1st, and a constant. If any of those is missing, then it has to be replaced with a 0. All right, so that's the polynomial division section of the test tomorrow. This one is asking us, is n plus 9 a factor of n cubed plus 14n squared plus 49n plus 36, and to justify our answer. Now, this is where we have to remember that if n plus 9 is a factor, that means that when we divide this polynomial, if we divide this polynomial by n plus 9, the remainder has to be 0. Okay, so it's a factor if when divided the remainder is 0. Just like with numbers, if we divide 12 by 3, 3 is a factor of 12 because 12 divided by 3 has a remainder of 0. So we're looking for a remainder of 0, and this one is really nicely set up to use synthetic division. -9, 1n cubed, 14n squared, 49n, 36. Skip a line, draw a line, bring down the 1, multiply and add. So that's -45. This is 4. That's -36. And that gives us a 0. And that does indeed prove that -9 is a factor. Okay? So justifying the answer would say n plus 9 is a factor, and you could simply say that it's a factor because -9 is a root. You could say that, or you could say that, because it is divisible by. Our original polynomial is divisible by n plus 9, meaning that the remainder is 0. All right. Now, the next polynomial that is, the next question is similar to this one. Is v minus 6 a factor of that? Now, you got to be careful with this one. We still want to see if 6 is a 0, because if 6 is a 0, then v minus 6 is a factor. But in this polynomial, we have 1v to the 4th, -6v cubed. We have 0v squares, -10 and 54. So you got to remember this thing right here is extremely important in this process, particularly when you're using synthetic division, because you don't immediately see a misalignment of terms with synthetic division. So 6 times 1 is 6. That gives me 0. 6 times 0 is 0. That's 0. Add those, you get another 0. That's 0. That gives you -10. And 6 times -10 is -60, which means we have a remainder of -6. Okay, so v minus 6 is not a factor because positive 6 is not a not a root. Okay? So that's how those problems work. And what I'm really just trying to make sure that you understand is that the relationship between the factors of a polynomial and the zeros of that polynomial. So our next section is going to deal with actually finding the zeros of polynomials. Or actually, I think maybe this section is just telling us to, let me look at the directions. The directions say just stating the possible rational zeros. Okay, so the possible rational zeros of a polynomial are the factors of the constant term divided by the factors of the leading coefficient. So the factors of the constant term, plus or minus 1, is the only factors of this, divided by the factors of the leading coefficient, which is plus or minus 1, plus or minus 2, plus or minus 4. All right, so what that tells us is, and I want you to list these individually on the test, the possible rational zeros are plus or minus 1. We'll get that from 1 over 1. Okay, the next set will come from 1 over 2. That's going to be plus or minus 1/2. And then similarly, our final pair of possible rational zeros is plus or minus 1/4. So that is going to continue for the next 3 problems, I believe. This one would be the factors of negative 9 divided by that. So the factors of negative 9 are plus or minus 1, plus or minus 3, plus or minus 9. And that's over the factors of this 9, which is plus or minus 1, same thing, plus or minus 3, plus or minus 9. So we've got our 3 top terms here, all divided by 1, right? And that's going to give us just those terms, plus or minus 1, plus or minus 3, plus or minus 9. Okay, then the other zeros are going to come from these 3 things divided by 3, which is going to add only one new factor, right? The only new factor that adds is going to be 1/3, because 1/3, 3 over 3 is just 1 again, and 9 over 3 would be 3 again. So there's no need to repeat those things as possible zeros. So plus or minus 1/3 is the only one we get out of that. And then the next we have 9 divided by these things. 9 over 1 is 9 again, 9 over 3 is 3 again, and then 9 over, I'm sorry, we did have, that. I'm confused here. I confused you. Kind of back up a little bit. 1 over these 3 things would give us also 1/9, plus or minus 1/9. I missed that one. Okay. If I could rewind this real quickly, I would do that. But dividing 9 by all these things is just going to give us 9 over 1, which is 9. That's already on the list. 9 over 3 is already on the list as 3. 9 over 9 is already on the list as 1. So that's my 10 potential rational zeros for that one. So this process is pretty simple if you remember that we're looking for the factors of our final term divided by the factors of our leading term. Now this one is different because we don't have a constant term here. We need a constant term to apply the rational root theorem, so we have to get that one, and you're going to do this anytime everything has an x in it. Our application is whatever the application is, whether we're finding zeros or sketching the graphs. The first thing we're going to do is factor out that x, which is actually a 0. X equals 0 is a 0. And we get this. Okay, so 5x cubed, this remaining polynomial, there's one of my zeros. So the possible rational zeros are going to be 0. and then the factors of this number divided by the factors of that number. So plus or minus 1 and plus or minus 1/5 potential rational zeros for that one. So if everything has an x, you got to remember then in every application that we're going to do, it's a good idea to factor that x out and then work with the remaining polynomial to find the zeros. All right, so that one's there. I think this one's the same thing, still stating possible rational zeros. So again, you would factor out the x times 4x cubed plus 9x squared plus 6x plus 1. And so our zeros are, possible zeros are 0, actually is a 0. It's not just a possible 0, it is a 0. And then the factors of 1 divided by the factors of 4. So positive and negative 1, positive and negative 1/2, positive and negative 1/4 are going to be the possible rational zeros, in addition to 0, which we already know is a 0. All right, so that gets us through that middle section. And then the next section is asking us not just to state the possible rational zeros, but actually to find all the zeros. So in this problem and in the next 4 problems on the review sheet, you're actually going to be finding the zeros, which means we're going to, again, identify the possible zeros first. So our possible rational zeros for this problem are the factors of this number divided by the factors of that number. And so that's going to give us plus or minus 1, plus or minus 1/5. So we have 4 possible rational zeros, and our goal is to find one of those using synthetic division and then go. So we're just going to start finding, seeing if 1 is a 0. If it is a 0, then it will give us a remainder of 0. That's what the remainder theorem tells us. So 5x cubed minus 9x squared plus 3x plus 1. Again, making sure that all of your powers of x are represented there. So 1 times 5 is 5. That's negative 4. That's negative 4. That's negative 1. And 1 times negative 1 is negative 1, which gives us a 0. And that means that the actual zeros, okay, are going to be 1 is a 0. The remaining 2 zeros, and the reason I'm looking for 3 zeros is because this is a 3rd degree polynomial function. And so the remaining 2 zeros are going to come from our quotient right here. And that quotient is 5x squared minus 4x minus 1. And I want to know where that's equal to 0, because that's going to give me my remaining zeros. I'm pretty sure this is factorable. We'll solve it by factoring. That's negative 5. The factors of negative 5 that add up to be negative 4 are negative 5x and positive 1x, negative 5 and 1. So I need a negative 1 here to get the negative 5x, and a positive 1 there to give me the negative 1x, or the positive 1x, and that's going to be negative 1. And so I've got that factored correctly, and the zeros of these 2 factors are negative 1/5 and positive 1. So we are finished with this problem because we have identified the possible rational zeros, and then we have actually found all the zeros of the polynomial function. All 3 zeros of this one are actually rational numbers, and you can see that they're indeed on our list. 1 is a 0 twice, which is going to affect what happens with the graph there, but we're not sketching the graphs of these, even though we could quite easily sketch this graph. All right, so the next example is to state all the possible rational zeros and then find all the zeros of this one. The possible rational zeros, again, come from the factors of this number divided by the factors of that number. So my possible rational zeros are plus or minus 1 and plus or minus 1/3. Then we're going to find those zeros, which hopefully you will be able to. I'm not going to give you one tomorrow that doesn't have any rational zeros. We're going to test these. Let's see if 1 works. and 3x cubed, 1x squared, negative 3x, negative 1, and 3, bring down to 3, multiply, that's 4, multiply, that's 4, that's positive 1, and it's our lucky day because 1 does actually work again. It gives us a 0, and the quotient, the remaining polynomial that we'll find the zeros for, are going to be 3x squared plus 4x plus 1 equals 0. And that, again, is a factorable polynomial. 3x and x for that. The factors of 3 that add up to be 4 are 3x plus 1x. And so this needs to be plus 1 and plus 1. And that means that my zeros are x equals 1, which we found here with synthetic division. And then negative 1/3 and negative 1 will be the remaining two zeros that we find from these two factors here from that quadratic polynomial that results. Now, again, we're not sketching the graphs of these, but this would be a really, really easy graph to sketch. Let's do it real quickly, just do a rough sketch. I know the x-intercepts are 1. Let's just kind of stretch this out a little bit. 1 is here. Negative 1 is over here. Negative 1/3 is somewhere in this vicinity. My x-intercept, my y-intercept is negative 1. There's my y-intercept. So it's going to be somewhere down here, right? And we know what a cubic graph looks like. This is positive x cubed, so it's going to look something like this. It's got to come down there and get that. It's got to come down here and get this, and then go up again. So that's just a rough sketch of what that graph would look like based on the zeros and the y-intercept, and the basic knowledge of what the cubic function looks like. Okay, next example. Again, we are finding the rational zeros. And again, the possible rational zeros are plus or minus 1, plus or minus 1/3. And when I start the synthetic division process, if I use 1, let's see, this one doesn't look like 1's going to work because I've got so many positive numbers, but we can go ahead and illustrate that. So that's 3, that's 3, that's 22, that's 22, that's 25. And you can see pretty quickly that 1 is not going to be a candidate for us. It gives us a remainder of 24, which is not 0. What we're looking for are these zeros. Now, if I were graphing this, 124 is a point on the function, but we're not graphing it at this point. Let's try negative 1. All right, so 3, that's negative 3, that's 16, that's negative 16, and again, I'm striking out. All right, that's going to force me to go into the fractions, which is not bad because that leading number is 3. So if we try 1/3, we would get 3, that's 1, that's 20, this is 20 over 3, 29 over 3, 29 over 9, that's not going to give me 0. So as fate would have it, it's going to be the last one that we try here that works. I could have reasoned my way into saying that a positive one can't work, but at least I'm hoping this one's going to work. So this would be 3. That's negative 1, which gives us 18. I like the looks of this because negative 1/3 times 18 is negative 6. That's negative 3. Negative 1/3 times negative 3 is positive 1, which gives me a 0. All right, now, so the zeros, I've run out of options, right? I've tried all my possible rational zeros, and only negative 1/3 works. Only negative 1/3 works. Okay, so the zeros are negative 1/3, and then the two zeros that are going to come from 3x squared plus 18x minus 3 equals 0. Now I want to immediately make this easier for myself and divide out the GCF. 6x minus 1 equals 0. And this is a beautiful candidate to solve by, drum roll, completing the square, because a is 1 and b is even. So x squared plus 6x equals 1. Half of 6 squared is 9. Add 9 to both sides, and that's going to give me x plus 3 squared equals 10, which, you know, if we cut to the chase, my two solutions are going to be -3 plus or minus the square root of 10, and that's that. Now, if I were sketching the graph, I would need to do a decimal approximation for those two x-intercepts in order to sketch the graph of this one. But that's the 3 zeros. They're all real numbers, and so there are 3 x-intercepts for this one. Okay, next example, x cubed minus 64. Now, this one is a little bit... Actually, it's a little easier than the previous problems, because if we remember back to our factoring skills, this will factor. This is cubes. So the cube root of x cubed is x. The cube root of 64 is 4. We're going to square, multiply, square. Signs are same, opposite, positive. So we could do it that way, and immediately one of our zeros is 4. The remaining zeros are going to come from solving x squared plus 4x plus 16 equals 0, which is, again, another great candidate for using completing the square, because a is 1 and b is even. So add 4 to both sides, and that's going to give us x plus 2 squared equals -12, which means x plus 2 is both square roots of -12, and the square root of -12 simplifies to be 2i times the square root of 3. So my 3 zeros are 4 and -2 plus or minus 2i times the square root of 3. If we're graphing, these are not intercepts. So this particular graph only has one real intercept, and that's x equals positive 4. Okay? Now, if you didn't notice that, you would kind of work your way through the synthetic division process. The first 0 that you're going to find is 4, but you might notice right away that 4 squared is 4 cubed is 64, and that's going to be a 0. So 1x cubed, 0x squared, 0x, -64. Bring down the 1, that's 4, that's 4, that's 16, that's 16, that's 64, that's a 0. And then again, you'll see that we still have x squared plus 4x plus 16 equals 0, which is the same as the polynomial that we just solved a moment ago. So the process is still the same if you don't recognize that it's factorable. All right, next example. This says to sketch the graph. Now, the difference here is that we're actually going to be using these zeros that we found, that we find as our x-intercepts, and the negative x cubed is going to tell us the shape of the graph. And so the possible rational zeros here are plus or minus 1, plus or minus 2, and plus or minus 4. That's the factors of this number divided by the factors of that number. So positive and negative 1, 2, and 4. And I'm just going to use the synthetic division process, and I'm not looking at the answers here, so I'm just going to use 1, which I don't think is going to work. Negative 1x cubed, 3x squared, 0 x's. There's a key right there. Negative 4. Bring down the negative 1. That's negative 1, that's 2, that's 2, that's 2, that's 2, negative 2. So that doesn't work, but by the remainder theorem, 1, negative 2 is a point on my graph. So I can kind of store that away and use it for later. Let's see if negative 1 works. If negative 1 is a 0 of my function, That's going to be 1. That's 4. This has got potential. That's negative 4. Let me clean that up a little bit. Negative 1 times negative 4 is positive 4, which gives us a 0 there. And then, so I've got 2 of my 3 zeros, but I also could have stopped earlier and factored this, right? I missed this. I could have factored this one or solved that one. So yeah, I really worked myself too hard. What I should have done right here is negative x squared plus 2x plus 2. No, that's not a 0. I couldn't do that. I didn't work myself too hard. I didn't. I'm innocent. All right, so at this point, this is the first 0 that I found. Actually, 1 is not a 0. Okay, this is my first 0. And this resulting polynomial, negative 1x squared plus 4x minus 4 equals 0, is going to give me my remaining 2 zeros. So I'm going to change the signs here. And that's going to be x minus 2 times x minus 2, right? So my 3 zeros are negative 1, and 2 is a 0 twice. Now, you don't have to list these zeros this way as separate zeros, but it is good to know that it's 0 twice because that tells us something about what the graph does. Okay, so let's go back and get our y-intercept. The y-intercept is where x is 0, so if these x's are 0, we're left with y equals negative 4. So the y-intercept is at 0, negative 4, and I've got 5 points here that I can use to help me shape my graph. 0, negative 4. My x-intercepts are at negative 1. 2 is a 0 twice, which means it does not pass through that 0. It just touches it and then turns back around. So it looks like this graph is going to have this shape. It's got to come down here and come up there and touch that and then turn around and go back down. So that's the shape of that graph. If you wanted to find some additional points, actually we did have an additional point that we didn't use. 1, negative 2 is right there. So I missed it a little bit, but this is going to kind of kiss there and turn back around and come back. Okay, so that's the graph of that one. The next example, sketch the graph of this. Now we're going to sketch by finding the zeros. That starts with stating the possible zeros are plus or minus 1, plus or minus 5. And we're looking for 3 of these. And so let's just dive right into the synthetic division process and try 1. 1x cubed, negative 4x squared, 0x, 5. Don't forget the 0. Bring down the 1. That's negative 3. That's negative 3. This is not going to give me a 0, but I'm going to continue the process because it does give me a nice usable point. When x is 1, y is 2. I could go ahead and just put that right there on my graph, and then it's ready for me when I want to use it. So let's try negative 1 and see if negative 1 is a 0. 1, negative 4 is 0, 5. Don't forget the 0. Bring down the 1. It's negative 1. It's negative 5. I like the looks of this. That's positive 5. Add those to get 5. That's negative 5. That gives us 0. And we have a 0. So negative 1 is a 0 right there. Okay. On the test, I'm going to probably ask you to state the zeros at some point. May even give you a place to kind of list them, just to make sure you aren't forgetting things. And then the remaining 2 zeros are going to come from x squared minus 5x plus 5 equals 0. And that's got to be solved by the quadratic formula. X equals the opposite of b plus or minus the square root of negative 5 squared minus 4 times 1 times 5 all over 2 times 1. And that gives us 5 plus or minus. Looks like 25 minus 20 is 5 over 2. Now, because I'm actually sketching the graph of this, I need to get a zero approximation for these two things, or decimal approximations for these two things. So 5 plus the square root of 5 is 11.81 divided by 2. No, that's not right. I did 5 times the square root of 5. Okay, 5 plus the square root of 5 is 7.2 divided by 2 is about 3.6, because these are just approximations. And then 5 minus the square root of 5 is 2.7 divided by 2 gives me about 1.4. So for my graphing purposes, these are my zeros. All right, so -1, 3.6, and what was the other one? 1.4. Now, another point that's going to help me is the y-intercept, right? So my y-intercept is +5, and we can see things taking shape. This is going to be shooting up from here. Somewhere it's going to turn around, pass through there, come back up, and pass through there, and go up again. That's what the graph of this function is going to look like. So you can see, hopefully, you can see how all the skills are tying together. The skills of synthetic division for evaluating the function at the root, and the possible rational zeros and actual zeros, and how those things translate into the graph. There's really a lot of repetition of the same skills that are being used here. Let's do. I don't know if we'll do the remaining problems, but let's do this one, because what's different about this one is that you should run into trouble when you're trying to think about what the possible rational zeros are, because there's no constant out here, right? 0 is the constant, which means only 0 is a possible rational zero, but that's not the case. What we have to do here is create a function that has a constant. So what I would do is factor out a negative x, because x can be factored out of all these things. That's going to give me this right there, I believe. Let's double check that. You could have just done x if that confuses you. So now we can see again that x is actually a 0. So my possible rational zeros are 0, plus or minus 2, and plus or minus 1. That's the numbers that I have to check. Now, you could check those in your original polynomial if you want to. You could check it in that one. That would actually give you some usable points, but you're going to save yourself some time if you just check it here. Now, because I can see pretty quickly that 1 is going to work. It's 1x cubed, 0x squared, don't forget the 0, minus 3x plus 2, bring down the 1, multiply, and add. And that gives us a 0, and that means 1 is a 0. 0 is a 0, right? And x squared plus x minus 2 equals 0 is factorable as x plus 2 times x minus 1. And actually, 1 is a 0 twice, right? X equals 1 here, x equals negative 2 there, x equals 1 there. So 1 is a 0 twice. And that means that the graph is just going to kiss there. So this is, let's sketch these things. So my x-intercepts are, hold on, have I made a mistake here? No. Our zeros are 0. 1 is a 0 twice, and then my other 0 is negative 2. So using what we know about negative x to the fourth, right? X to the fourth has this general shape. Negative x to the fourth has this general shape. So this thing is going to come from down here. It's going to pass through that one, come back up, just kiss that one, and then go down. So that's what our graph is going to look like there. Just a rough sketch. Okay. If you wanted to fill in some points there to add a little bit more shape to the graph, you could, but that's what it's going to look like. And again, the fact that 1 is a 0 twice is what tells us that it just turns around there. It doesn't pass through the 0. It only the function doesn't change signs there. Okay. Let's see if there's anything. Same thing with this one, right? We're going to first factor out a 0. X equals 0 is a 0 because everything has an x. And then the rest of the possible zeros are plus or minus 1 and plus or minus 3. And I have a 4th degree function here, so when I'm checking for these things, and I believe 1 is going to work, I'm only going to be checking this. All right. So if I plug 1 into that function using synthetic division, 1x to the 4th, 0x cubed, negative 4x squared, 0 x's, and 3. That's going to be 1, 1, 1, 1, negative 3, negative 3, negative 3, negative 3, 0. And we've worked this problem now a couple of times in class that ends up like that. And you'll kind of see that you run out of a lot of interesting, different kind of problems. So you'll start seeing a lot of these over and over as you practice. But if you finish solving this, you could solve it by factoring. Negative 1 is a 0 again. Let's just see it through, just like we've done before. Negative 1 is the next thing I would try, and I'm going to try it in this remainder that I have there. So that's negative 1, that's 0, that's negative 1. No, that's 0. That's negative 3. That's positive 3, which gives me a 0 again. And that leaves me with x squared minus 3 equals 0. So x equals plus or minus the square root of 3, which is approximately plus or minus 1.6. So I've got 4 zeros. 1, 2, 3, 4. If we plug those in, 1, negative 1, negative 1.6, positive 1.6 was w to the 4th shaped like. Actually, this is a 5th degree polynomial. I forgot about the first 0, x equals 0. So we've got there a 0 right in the middle. Is this negative? No, this is positive x to the 5th. The 5th degree function looks like this, right? It's got humps in the middle. So it's going to start from down here. It's going to go there, 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 and then back up. Oopsie, I didn't mean to curve like that, but the sketch will look something like that. Actually, it should just shoot straight up. It's not going to curve back. If you wanted to get a little bit more shape, you could plug some values in there to find it, but I'm not looking for a whole lot more detail than that. So that's what the graph of that one's going to look like. That's it. That's the last problem. So we've worked through the review sheet. Remember for the test tomorrow, you're going to have 2 days to complete the test, so just make sure that you work hard both days. And again, you can reference this video or reference the review sheet with your peers as often as you like, but you cannot discuss any of the actual test problems between Thursday and Friday. I wish you well. Make wise choices.